Okay. Huh. All right. Tuesday or Thursday, we'll just collect them in class. When things, oh, I have to close down. I liked hearing what you were doing. That was nice. But I have to close off that beeping. I liked, probably we'll have Monday, before class. We'll set up boxes before class and we'll start lecture. We'll start lecture with on days, first assignments that are due on days that don't have lecture, we'll post an option Fisher. And just have it there on sometime before we see. All right. The concept we got initially over here says no. Sometimes we get both. So just some people are working by themselves. And it's about 2 to 3 days worth roughly. And that sounds maybe like a fair amount. But by the time we get there, if you look at it, handouts for 2 weeks ago, which is not very hard anymore now. So you'll find that the stuff that you're doing now that seems hard to do. So there's going to be the structure, but also questions about the counter code, how that works. For the handouts, the handouts are learning happens. So anything, so go learn. Okay, so when it comes to counter code violations, so as long as you don't actually cut and paste someone else's code and written answers and include it as your own, you're fine. Look at each other's code, work together, work in groups, collaborate, build up. That's where that happens. With the handouts, we also have preset assignments for additional reference. That's what those are for, that's what we need the solutions does. Feel free to start with any of our code. You don't have to go, you don't have to start from a strict every time. Start with some of our code, just variable, we're talking about that. Start with some of your earlier things you don't know. Please, that's what I need to say. And then other code rules for the problem set. The rule is you can talk with other people, but not with their code. Does that make sense? Just as like a ground rule for the problem set itself. Talk with other people as much as you want. You'll find the process can split into 2 parts. So the first part is just a series of questions about what it's going to be a paragraphs study. And then we're going to say, well, what's the internal loop? What's the external loop? What are the potential outcomes? So you know, just like the stuff we did through marketing lecture, we'll be expected to write on the order of 2 to 6 sentences for each 4 questions. Okay. I'm particularly parsimonious in my writing. So you can write it in 6 words, you can write it in some people just like to write a lot. Try not to go over 6 sentences, just because we have a lot to write. There's some people, we're not writing the questions, we multi-paragraph essays. But we do accept punctuation, you know, these should be proper sentences. Then in the coding part, you can talk with each other about that. Talk through the ideas, whatnot, just obviously don't copy each other. Okay. Then with the code, just don't copy each other's code. Don't look at each other's code for the process. Just use the code on your own or with your partner. With your partner, you can do things like share code, obviously, because you're working on one document, but you don't share it across groups. Are there any questions or clarifications regarding the problem sets, honor codes, etc.? Okay. If additional questions arise, just send me an email or raise your hand or some, you know, just be in touch. All right. So for today's lecture, we're going to talk about different types of variables, quantitative and qualitative variables. And we're going to present a method for how to summarize unidimensional data, which is this. How can we characterize a single variable? This is going to be the first lecture where we're going to discuss figures in a way that I expect you to be able to turn around and think about the same figures. So we're going to get some classic histograms today. But to orient you for just a bit, before we're spending a lot of time on figures and plots and how to make that appealing and informative before we ever get to statistical significance or p-values or standard errors or confidence intervals or all of that. The reason for that is because figures should convey your story and figures. The regression is important. We'll talk about why it's important down the line. But I've never seen anyone's mind changed by a regression table, but with the right figure to illuminate the problem and illuminate your claim. The reason for that is that figures make the data visible to you. Okay? So the nice thing about figures is they convey the raw data without any particular assumptions or not too many assumptions. And what I'm going to encourage everybody to do for your JP or senior thesis work is always include a figure of your raw data. In some fashion, or several figures, it could be 2 by 2 or something like that. But the idea here is that you should be able to convey your basic point by looking at the raw data. Whatever you're finding in the data should be visible to the data. Then when you're done with it, you go through and we'll talk about regressions and all the other things you have to do with p-values and significance and like that sort of thing. But I want to emphasize that the most compelling rhetorical technique in quantitative design is a figure. All right. Sometimes the figure is a flowchart of how you gather your data. I encourage that if you do it in an innovative way. Sometimes it's the results, it's the data themselves of how you result. And by the end of the lecture, the last thing we're going to talk about is the difference in difference design. And I'm going to convey the basic points of the paper just using pure core figures. And I want to listen to the power of this sort of analysis. By and large, if you're doing a study and you find a result that's statistically significant, we'll get to that in the first semester. But you don't see it in the data, beware of the result. What we're looking for are results that are visible when you plot them in some particular fashion. Now, in particular fashion is doing quite a bit of work in that sentence. So I'll be exposing you to 3 or 4 different types of plots that are sort of standard go-tos, but there's lots of room to get creative here to convey your work. Now, the first thing we're going to talk about are different types of variables. So, a variable is just a characteristic of an observation that these different values across observation. A variable can take on the same value for every observation because then it doesn't vary. So it's just some attribute of each observation. An important early distinction of this course is between quantitative and qualitative variables, or just quantitative and categorical variables. A variable is quantitative if it's continuous. So the quantitative variables are things like temperature or this could be, I don't know, how far your house is, or how far you are right now from where you are, or something. But by a continuous variable, it just means that it takes time finding your values. I was in a conference once where someone raised their hand and asked me okay, is it generally continuous if I can actually slice it down to like leptons? And I'm like, really? Mine's continuous. We're just going to let it be continuous. That was not your question. So these are things that are used in measurement. We may want to distinguish between continuous variables and discrete variables. Where discrete variables take out values of the natural or whole numbers. So these are variables that only take on values 0 or 0, 1, 2, 3, 4 or something like that, right? So just quantitative continuous variables are things like your height inches or your height centimeters. Discrete variables, how many of those again? No one has two-thirds of the system. Okay. These things have values 0, 1, 2, 3, 4. Continuous variables may be measured discretely. What does this mean? You may want to take for a cover study that takes a continuous variable like income and just separates it into bits. Low, medium, high. Or deciles, right? Or just splits up to 10 different groups based off the distribution. But we can course in continuous variables, and sometimes that's useful. There are reasons why this may be useful. We may not trust in everyone. So I'm working with some data for degrees. And the data has predicted income for folks in North Carolina. I'll tell you about that second. We'll come back to this semester. But this particular income measure is predictive. It's literally what the transmitted and forecast stuff that are the short contribution to your income. It's that. And we don't trust it exactly. Because it's not the number that's recorded to the IRS, it's the number that's computed from some model right here. So because we don't trust a continuous measure, we fit it into colors. And we say, low, medium, low, 1, 2, 3, 4, 5, and lows and highs. So there are times where you might want to discrete highs, and it's very cool to make that work. The second type of variable that we're going to talk about are qualitative or categorical variables. Qualitative, so for the variables, the quantitative variables, they have some sort of order. Okay. So in this case, if one person has one sibling and another person has two siblings, the person with two siblings has twice as many siblings as the other person. All right. That's to be distinguished when we first came up with this. That's to be distinguished from categorical variables, where if you do something by religion, right? One might be Protestant, non-Catholic. One might be, two might be Catholic. Three might be Muslim. Four might be Jewish. And there's no argument. No one's claiming that 4 is close to, right? Those numbers are simply placeholders for different groups. And this showed up in the top of the data we were looking at. So in this particular setting, categorical variables are just basic categories. It's important in order to know which variable, type of variable you're talking about, because R treats them differently. And you can tell R is treated as one type versus another. In R, a quantitative variable is considered a numeric option. That just means it's given 16 or 32-bit representation on B. It's just treated as a number with like 16,000 places. Okay. Qualitative variables are considered factors. And what that means is it just treats each level as its own variable. So if you represent a qualitative variable as 1, 2, 3, 4, 5, R differentiates between treating those as numbers and treating those as just names of unordered categories. If it's a factor type, it's the name of unordered categories. Where is that coming? I'm just to go back to the top first data with that one argument of race. That was obviously categorical. If you don't tell R as a categorical variable, it will treat it as numeric and it will end up getting some absurd possibility as a result by your analysis. Common data formats. The two types we're going to talk about, the most common one I think we use are CSV files or common separated values. If you see a CSV file at some point, just go to the property, open up and look at it. all it does is the first row are the variable names. And that's what we told you to read the header. The second row are the values of each variable, separated by commas with the invisible line break. You can't see it, but it's there. And all R is going to do is read in one line at a time. And what it actually does is it reads in the first 7 lines to make sure that there's the same number of values in each of the 7 lines. Then it infers how many variables there are in the CSV file. Then proceeds to read it in line by line. We'll take care of that for you in this course. But for a good time, ask one of your preceptors about funding and cleaning data. And then just sit back and smile because you're not going to be cheaper. We're focusing on a particular part of data analysis in this course, but we're giving you data that's fully formed and packaged and will be read. When you go to your own work, most of your work is going to be either gathering data, which is a ton of time for creating that, or merging data from multiple sources, which is just a massive headache most times. So just be ready for when you start doing that and some time for your analysis. We're working in a world where you have a data set that we are, and then we start analyzing. All right. In these files, not everything needs to be separated by a comma. You'll find tab delimited files or space delimited files. I don't like space delimited files because sometimes you have a space in a variable name that will throw off. So I think we're going to save mostly the CSVs and have separated files. All right. Just some things to be aware of. Now, we're going to talk about 2 different types of measurement error. And I'd like you to be able to differentiate between them. The first type of error is random measurement error. The second type of measurement error is systematic error. And it is wildly important to be able to distinguish between these 2 types of error. So let me ask you a question. Over the last 2 weeks, just call out a number. Over the last 2 weeks, how many times did you eat breakfast? Over the last 14 days. 14. Wow, you're all right. Anyone going to hold solid 4 or 6? Okay. Any 3s or 5s? Okay. 14. Wow. So when I ask this question, and it is an utterly fair question, for a social sciences or study, the effects of breakfast on happiness or something, right? Our researchers might very well want to collect this data. Is there any reason to think that that number is exactly correct for everybody? No. Right? I mean, like when I said, who did it 4 times, it would shock me to make sure it was 3 or 5 or 6. But it's probably about 4. So the first part of measurement error is that the true value differs from what you're looking at. And this is often the average sums we call. When we talk about random chance error, I have no reason to suspect that people are reporting value above the literature. Right, so if they're misremembering, and I say, how many times did you have breakfast? And you said 5, I have no reason to suspect the answer is more likely to be 4 than 6. And it's probably 5. That's not the sort of thing you worry about. Systematic measurement error is the case where the data you're looking at, or the variable you're looking at, isn't the truth, and we suspect that it might be systematically above or below the truth. This is the one that's really pernicious. Random measurement error, if you collect enough data, its effects go away. Systematic measurement error, the more data you get, the problem persists. So, let's see. We'll talk about systematic measurement error in a moment, but it shows up quite a bit if you ask people in comparison, or potentially socio-technical questions. We'll talk about this later in the year, but if you go door to door, go, review basis. Really? Why That's not the sort of thing that normally happens, except there's been a lot of literature coming out in America that seems to. All right, we'll talk about that study. But if you go to Northern Rome, actually ask that question, you actually get a that's a different conversation. But I read studies, and some of my students are working on studies that deal with sex workers with HIV. Right? That's not a burden. I'm sorry, are you a sex worker? Are you HIV positive? Right? You're just not going to get into the economy. Dealing with undocumented immigrants. These sorts of questions, if you ask these questions, we don't suspect that the answers are going to be commensurate with that people are going to misrepresent in one fashion or another. We'll talk about one example of this. Oh, so that's misreporting in surveys. Sometimes that's termed social desirability bias, where I don't know, I'm just trying to think of a good question. Do you ever shower? I don't know. Right now, I'm thinking about no. People are biased towards saying that's on that. Sometimes government statistics in some countries will suspect that bias. Some countries are more reliable with their statistics than others. Some fabricate data entirely. The stories of the GDP of this former Soviet Union are insane the way to gather statistics and reporting that happened there. Another type of systematic measurement error is interpersonal incompatibility in surveys. This is a subtle one which has been coming out in the last few years of surveys. But this is one where, like, I asked you on a scale of 1 to 5 being amazing, 1 being horrible, how's your day going? And you say 4 or so. But the question is, does your 4 mean the same as someone else's 4? Let's say I go to a war-torn region and ask that, so I'm going to 4, right? And that's the interpersonal compatibility. Those sort of 1 to 5 scales, like, how are you doing today? How are you doing this? Unless you ground it to an objective measure, the 1 to 5 measures don't really communicate much with the average across individuals, because one person's answer or 3 might not be someone else's version to create an objective sense. Okay. We'll get examples of that as well. But we're going to start by talking about social desirability bias. This paper, about 10 years old, but I pulled it out because it was particularly important in picking up a lot of work in political science. America's fascinating in all sorts of ways. One of them is we don't know how many people in this country are eligible to vote. And our surveys don't tell us much about who did vote. So this has habitually been the case for decades. When we send out, when folks would run surveys and say, did you vote in the last election? Do you think people are lying and remembering reporting their voting or reporting that voting? About 100% twice. Because what you can do is actually just survey everybody in the state. You don't get a couple hundred people. You are about 1,000 people. Say, did you vote? And generally speaking, the answer to that question is about 10% higher than the actual voting. Why? So you try to realize people just report voting much more than they actually do. The issue with that is that we use things like did you vote from survey data in a lot of studies in political science. Explaining why people vote is kind of like one of the bigger things we do as a field. So for data on trustworthy order view. This is early order that takes the reported votes and the validated votes from individuals. So this comes from the CCES is the Cooperative Congressional Election Study. And it's a study of thousands and thousands of people every 2 years that are scientifically work about 20 years. And it gives us a large N sample, so thousands of people every year. With a fair number of each state, it just asks them variety questions. One of the questions it asks is, did you vote? And then as per normal, the number of people who reported voting was much higher than those that actually did. So what this particular paper was it went to Catalyst, which is a massive voter file, it's a private voter file. When campaigns pay a lot of money for these voter files, because it takes the data from each state as to who lives there, who voted in registration, and merges it with credit score information. And it merges on individuals, and it's as difficult processes you want to catch and how to do it more closely. And what they did was they just said, well, we know the names of the people we asked, did you vote? We also have the records from the state, did they actually vote? And how misleading are these results? So taking a look at this, we're going to look at the CCS, that first column. And we're going to look at columns 5, 6, and 7. And in this case, column 5 says the probability that someone reported they voted, given that they could find a record of this person actually voted. That's what that first column is saying. That's a 99.1. That means 99.1% of people that the authors would show actually voted report have voted. In row 6, we see the probability of a reported vote giving a value did not vote. So in this case, they went back to the data and took everybody who didn't vote, went to their survey and said, of the people we surveyed who I know didn't vote, what proportion of them reported voting? And the answer here is 52%. Half the people that said I didn't vote, sorry, half the people who didn't actually vote reported voting. The last one's the probability of a valid vote given a report vote. So the way we sit, the way line 7 works, is it says, amongst everybody in the survey who reported voting. So I call them up the 26,000 people. And I say, did you vote? Among those who said yes, what are the probability that what proportion of those actually voted? And the answer is about 80.6%. So if you call people up on a survey and say, did you vote? And they say yes. If you go to 5 people and say, did you vote? And the answer is yes, one of those probably lied to you. Okay. This is the beginning of pushing our field to using validated voter files. And that's now the norm. If you go to the upshot on the other times. If you go to the comments, that's one of our comments, doing a lot of those right there, comments. And now people aren't trusting surveys on voting unless it's validated in this order. And this data, while excessive, is out there, and firms are using it. Firms and campaigns are using it. But here we have an example of social desirability bias, because the authors then go through a bunch of canonical political science studies and find the results to be a little shaky, using validated vote rather than reported vote. Now what we're going to talk about is we're going to switch to our social desirability bias and shift over to the representing continuous data. And basically we're going to build up to histogram. So this data is just the GDP per capita of 180 countries, the links there. And what we're going to do is just take the countries, 180 countries, and represent them as a table. We could list out all 180 countries in sort of order, but that's like pages and pages. So what we do instead is we're going to create a set of pins. Equal with, and we're going to put the number of countries in each line. So the way to read this table, this is just a way of presenting a single variable. 97 countries have an average GDP per capita of less than $10,000. 38 countries are between 10 and 19, 17 are between 20 and 30, 16 are between 30 and 40, and so on. And 1 is between 80 and 89, or 1 is between 80 and 90. So all we're doing is we're taking this continuous variable, splitting it out along its range, and just counting how many observations fall in each year. It's a table. There are times where this sort of presentation is useful. But a more informative approach would be to present a histogram. Okay. Histograms, folks have seen histograms before, right? That's like middle school tutor, right? Like you've done see. We're going to dig into it a little bit, and I'll give the presentation here for those folks who weren't exposed to it. But we're going to go with histograms to plots to resolve. So a histogram is when we take continuous data and we split it up into bins like we have that table. But then we create figures where the height of each bar is proportional to the number of observations. Okay. The bin interval length times the bin height sums to 1. This is called a density scale. And I'll show you what that means in a moment. So the previous table can be represented like this. Generally speaking, it makes more sense if you present one variable to a histogram just more visually. The y-axis is the density scale. The x-axis is the variable itself. And what I did was I put the height on the density scale on top of each bar to show you that those bars are going to add up to 1. There's a total mass of 1 or a total area of 1 underneath all those bars. So now for those below, each bin has a limit of 10. So the density scale that capture the width times height of the two bars added up is going to add up to 1. The point here is that we can take any two variables and represent them on a density scale for comparison purposes. And we'll do that in a few slides. But for now, I just want to highlight that we can represent any variable on a density scale. The biggest critique, and I'm a fan of histograms, but the biggest critique is that we don't necessarily have a direction. Right, and it's 0 to 10, 10 to 20, 20 to 30, that seems reasonable. But it's possible to put the bins too close or too far. And so we're trying to characterize GDP in the world. If you look at one set of breaks on the left, in that one, the breaks actually go from negative 5,000 to 10. Just because. And then they sort of even out afterwards, but if you look, it sort of tapers off, up and down and up and down and up and down a little bit. With a different set of breaks, the ones on the right are the ones we did. Where I'm going with this is that it's possible to adjust the bin width in histograms in order to get different stories. This is what I'll point out a little bit more clearly. On the left, the bin width, if you look at the thin breaks, the story seems to be that very few countries have a very, very small GDP per capita, and a few that it shoots up, and it goes down, and down again, and down again, up and down, and up and down. And there's something about the left-hand side that just doesn't seem to be. The one with the thicker breaks is a little better, but there's actually some interesting statistical theoretical work as to how many observations you can share to start to put us to bed. And then if you look at one on the far right, you say, well, there seems to be 3 types of metrics, mostly in the high. And what I want to warn you about with histograms is just be careful, because the breaks, generally not for malfeasance, but sometimes just through lack of care, the breaks can be misleading. It's possible that the breaks in one place can tell one story, and the breaks in another place can tell another story. That's it. So when you see a histogram, just have your break down a little bit, and just go, is this actually what's happening in the grid? One way that people get around this increasingly is they'll put a hash mark on the bottom for each data, so you can see where the actual data is. And that's one thing that people can do. Another solution, which you're going to hit in a handout, is using a density. So what a density does is smooths over histograms. So in this case, it smooths over histograms. So what that means is it says, well, the true bin width might be really wide, so let's calculate that. Now we take the true bin width to be really tiny to calculate that. and it sort of averages over a distance. And what that's going to do is create a smooth density plot like this. Another way to think about this is it creates a big point. So one of the things it does is it says, well, I'm going to take the value of 40. And I'm going to look 5 to the left and 5 to the right if you already record that number. But just to get it constantly over the measure. Okay. I recommend using density plots as the first cut for presenting the data. Simply because it conveys not just where the center of the data is, but what it looks like. And it's a pretty reliable. So this shows there's a peak somewhere around 5, and then maybe another peak around 40, and then it tapers off a little. But it tells me something about the entire distribution of the data. Now we're going to talk about, oh boy, I take the word recently off that slide. But now we're going to use density plots to talk about other very important stuff in social sciences. That people here. Use how it's in the mathematics. And it's going to deal with the rating minimum. If we follow sort of the naive micro kind of 101 sort of method, which I think is not supposed to 101. Which one's micro? 101. I'm not projecting this out to be 101. This is very big to 100 recently. But there's a question, do we raise the minimum wage, right? There's fight over goes $15 on the floor, pushing for, some are pushing for 17. In this state, it's 13, in some states, it's 7, you have national, but like minimum wage is still an important issue. And one of the concerns is that if we raise the minimum wage, there will be fewer jobs. To some extent, that just follows directly from the idea of right? It's going to be more expensive, less of it is purchased. If labor becomes prohibitively expensive, there's going to be fewer jobs, especially the lower end where minimum wage rise. So that's an interesting theoretical on that. But there's an empirical side to it as well. When we raise the minimum wage, do the number of jobs go up? And that's what we're going to look at. We're going to look at this early 90s study for the results of this sort of persistence that we're talking about. So here's what POL proved in early 2013. Now you might argue that even if the current minimum wage is low, raising it would cost jobs. But there's evidence on that question. And while there are dissenters, as there always are, and there are good faith dissenters on this, the great preponderance of the evidence of these natural experiments points to little, if any, negative effect of minimum wage in unemployment. And what we wrote this paragraph is very clearly talking about the people who are about to discuss and the subsequent papers that are looking at this analysis. So let's go ahead and take a look at this study, set in New Jersey, actually. The paper is from Harvard for 1994, and it was a natural experiment. Right? So recall that a natural experiment occurs where we can start to make causal claims, at least under assumptions. But we can make causal claims because there's a randomization that's done in the real world that the researcher does not control. And the design of this was that in 1992, New Jersey raised its minimum wage from $4.25 to $5.05. And then Eastern Pennsylvania, we're going to look at Eastern Pennsylvania, raised its minimum wage, kept its minimum wage to $4.25. So you folks see the natural experiment happening there. If you go up and down the Delaware River, on one side of the river, the minimum wage went from $4.25 to $5.05. And then on the other side of the river, not about 100 feet away, the minimum wage stayed the same. All right? What the authors wanted to know was, did this increase in the minimum wage lead to a decrease in jobs? Specifically, well, we'll talk about what they do. But the authors implemented a this design called difference in difference. And there was a question last lecture about, well, can you use the previous time period as a baseline? The answer to that, we do that in this difference. So in this case, the first difference we look at is New Jersey after minus New Jersey before. Okay, so what happens to jobs in New Jersey after minimum wage minus New Jersey before? Now, can we just look at New Jersey after minus New Jersey before? This is called the before after time. If you do that, you just look at New Jersey. The answer is no. Why? Because New Jersey presumably raised its minimum wage for all sorts of things, for all sorts of reasons. And although the unemployment or the job level will be something, the entire economy is still competing with Africa. There's lots of other things going on. So what we're going to do is treat the difference New Jersey after minus before as our outcome. And we're going to take as our control group Pennsylvania after minus before. And say, I need a good estimate of New Jersey if it didn't raise its minimum wage. And to do that, we're going to turn to Pennsylvania, which keeps the same minimum wage, but look at its after minus before during the same period. So in New Jersey, our treatment is administered, and we look at the change in employment. In Pennsylvania, no treatment is administered, and we look at the change in employment, and we're going to separate, and we're going to take the difference of those two differences, which is why it's called a difference in differences. All right. In that sense, Pennsylvania after minus before is serving as a control group. It's serving as the baseline of what we think New Jersey after minus before would it look like if it didn't have the raising minimum wages. So we're turning to Pennsylvania to provide us a baseline. Now, has anyone been along the river between New Jersey and Pennsylvania? There's some really cool towns, really great. If you've been to Lambertville, amazing barbecue up there. Really good food, and it's a little resort-ish type town. There's New Hope on the other side of the river. If you have a chance, I recommend getting over that way while you're here. But what we're going to do is take a look at the results of these studies by we might kick off with this in the next lecture. I just want to ask one question and keep this going. When you do this sort of analysis, what sort of concerns do you have about the design of this study? Or what should the researchers be doing in order to maximize the internal validity of this? Yeah. Sorry, someone say that again?
There are a lot of differences between states. Like, if some people who are in the kind of jobs they're offering, so making sure that they're controlling for like what specific jobs they're looking at.
Yep. And the data we're going to look at, so we want to compare, so we want to make sure we're looking at the same sorts of jobs and same sorts of, right? Dealing with the same sorts of jobs, the authors here look at fast food employment. So they go a couple miles in from the Delaware on each side and measure the fast food employment. They do a survey on both sides of the river. But a concern might be what type of fast food, right? Because Burger King is okay, but like it's not. Roy Rogers, it's kind of funny going back because I got Roy Rogers there, a bunch of like, this might be in the study trip for me, but for not you. But like a bunch of like early 90s fast food firms that are not anymore. But it could be the case because each of these firms has, each of these fast food types have different kind of products. We might only want to look at burger, right? Or what we might want to do is just do it within each fast food firm and then average up across that. But the important part is we want to make sure we're talking about the same sort of job. And not everybody in the fast food restaurant is doing the same job. So we want to make sure that we're talking about the same sorts of jobs on both sides. The next question we're concerned about is talking about the same sorts of people on both sides. How would you get that? Yeah.
Cost of living. So if they're talking about the city or like a rural area, it can cost way different amounts of money to just live or survive.
So it's the case that if you go to, if you do the comparison by Philadelphia and Camden, which are right across the river from each other, but the Philadelphia side is massively expensive and Camden is really not. then you might not want to include that in the study. Whereas if you go to Trenton, Morrisville, they're a little bit closer demographically, but sometimes the river, the geographic boundaries, the political boundaries of the United States, have real differences on both sides culturally, but economically. So you might want to restrict yourself to area comparisons that make sense long term, right? Other thoughts on this design? What else would the authors need to do to make this convincing? So the question here, that's one of the make sure that we ask something. Oh, so the effective rate, so you can actually go up and down both sides of the river and see what the neighborhoods look like both sides, but the people might not be living near where they're working. So when you go to run these surveys of people in these restaurants, you'll want to gather characteristics, including rates, but also education, all these things, to make sure that they're comparable on both sides. And to do that, we do a balance check. We just calculate the means of each race on both sides of the river and make sure it looks the same. What else might you want to know when you have this convincing?
Politically or economically.
So in that case, so we want to know politically what's happening there. In the sense of, did the fast food industry lobby then Governor, I think it was Christine Hunt, if someone wants to check that, please. But was there a fast food lobbying group encouraging or discouraging a minimum wage adoption on both sides of the river? Right, that's the sort of thing. There's a potential political story that we obviously look at. Other questions? Yeah. Yep. So what are the workers' laws, unions, and just generally workers' rights and employers' rights? What do those look like? And enforcement on both sides. All that said, we're about to get to 20. We'll conclude with these next few slides next time.